Hello everyone, I am Divya, Assistant Professor, Department of Computer Science and Engineering. Today we are going to continue our discussion about the network layer. Okay, as far as the previous classes are concerned, we have discussed addressing and forwarding with respect to a broader perspective. We haven't discussed addressing and forwarding process with respect to any particular computer network, right? Today we are going to study about forwarding and routing with respect to a specific scope, that is internet. Okay, today we are going to learn about addressing and forwarding with respect to internet. When I say internet network layer consists of three major components. The very first one is IP protocol, that is internet protocol, with the help of which we are going to design our datagram. Okay, and next the routing component, which specifies the path through which the datagrams flows from source to a destination, right? And then we need to have a facility which is going to report errors if occurred during the transmission from sender to receiver. So we need to have a system or facility through which we can report the errors, and it should respond to the request that is being made by network information, right? So these are the three major components that internet network layer is having. Okay, when I say internet protocol, internet is going to perform addressing and forwarding through internet protocol. Okay, so it's going to perform addressing and forwarding through internet protocol, which we call it as IP. In IP we have two versions, that is IPv4 and IPv6. Initially we started with IPv4, which had 32-bit space for IP addresses, right? But due to the enormous increase in the number of users who are accessing the internet, it has gone out of the range. So in order to handle that issue, IPv6 is introduced. Now, nowadays most of the systems are making use of IPv6 for their internet protocol. Okay, so according to your syllabus we are going to learn more about IPv6. Okay, we will see how exactly IPv6 works, how exactly IPv6 datagram looks like. Okay. In the early 1990s, Internet Engineers Task Force started developing a new protocol or a new version of protocol, that is IPv6. What is the motivation for this? The prime motivation behind discovering or inventing a new version of IP or internet protocol is that in case of IPv4, as I already told you, we had 32-bit space for source and destination IP address, which was not sufficient as the number of users who started using internet has increased enormously. In order to support the growing demand for IP addresses, a new version of IPv6 has been introduced. Okay, so this is the datagram format which IPv6 is having. Similarly, we have datagram format for IPv4 also, which you can see in the diagram that is displaying. Okay, that contains various fields which has been removed in order to optimize the datagram format in case of IPv6. Looking at the fields here, the total breadth of this datagram is 32 bits. Okay, the very first field here is version. This is 4-bit. This is of 4-bit length, which specify the version of IP, the internet protocol that we are using. It can either be IPv4 or IPv6. In case of IPv6, the value will be 6 here. In case of IPv4, the value will be 4. Why we are having an option for IPv4 and IPv6, I will tell you in the later sessions. Okay. The next field is traffic class. Okay, this is 8-bit field which is used to specify the priority, okay, which is used to specify the priority for given datagram. Okay, by specifying the priority in the traffic class, we can make a datagram to travel faster from source to destination over other datagrams. Depending upon its priority, the traffic class field will be filled. Okay, the next field is flow label, which is of 20 bits length, which specifies the flow of the datagram. Here, in case of IPv6, there is no clear distinction or definition about flow. For example, we can consider video and audio streaming as flow. Okay, we can consider this as a flow, whereas our traditional file processing system or our file transfer protocols, all those things might not be considered as flow. So, the datagrams which belongs to different applications might be having different priorities, right. So, that priority can be set in case of traffic class based on this flow label. Okay. The next field is payload length, which specifies, this is 16-bit, okay, 16-bit field which specify the number of bytes. Okay, this specifies the number of bytes that actually present here in this field. The number of bytes of data that is present here in the field after the fixed 40-byte header. Okay, totally this constitutes 40-byte header which is of fixed length. After this 40-byte fixed length header, what is the amount of data, payload data that we are going to have in this particular datagram is going to be specified in the payload length field. After this, we have a field called next header which is of 8-bit length, which specifies to which protocol this datagram is going to be delivered to. Okay, after traversing from source to destination, to which protocol this particular datagram is going to be delivered to. The protocol that can be UDP or TCP, the different layers. Okay, so which comes under the different layer, that is transport layer, right. We have these two protocols under transport layer, right. In the next header field, we are going to specify to which particular protocol we are going to hand over this datagram once it reaches its destination. The next field is hop limit. Once again, it is a 8-bit field which represents the number of routers or the number of nodes that this particular datagram has to pass through in order to reach the destination. When the value of this hop limit reaches 0, it indicates that the datagram has reached its destination and then the datagram is dropped from the network. Okay. So, that is about hop limit, and the value that is stored in hop limit field is going to be decremented by 1 at each router. For example, if you have around 6 routers that need to be passed through between source and destination, then when a datagram passes from source to the first router, then the value of hop limit decrements from 6 to 5. Similarly, when it passes through one more router or one more node, it will be decremented to 4 and so on. When that becomes 0, it is indicated that the datagram has been reached the destination and that particular datagram is dropped there. Okay. That is about hop limit. The next field is source address, which represents the IP address of the source, okay, which is of 128 bits length. Okay. Similarly, the destination address to which this particular datagram has to be delivered, this is also of length 128 bits. So, this is the major field which is being included in case of IPv6. In IPv4 also we had source and destination address, but they were of 32 bits. Okay. Here they are of 128 bits to make sure that the word does not run out of IP address shortage. Okay. So, this is about the datagram format that we have in case of IPv6 datagram. Okay. Next, Keeping these things in mind, we will discuss what are the changes or what are the new fields that are included in IPv6 datagram, and then we will change which are the fields that were dropped from IPv4, the fields which were in IPv4 datagram but not in IPv6 datagram. Okay, we will discuss about that. Now, we will look into the changes that were introduced in IPv6 over IPv4. Okay. So, what are the changes that were introduced in IPv6 over IPv4? As I already told you, in case of IPv4 datagram header, we had 32-bit space for source and destination. And the major concern in early 90s were we were running out of IP addresses because of this 32-bit constraint. Okay. So, the expanded addressing capabilities were introduced by making 128 bits for both source and destination address. Okay. So, with the help of these 128 bits allocated exclusively for each source and destination address, the addressing capability is increased, by which we encountered the problem that we were facing with 32-bit space that was provided in IPv4 datagram. Okay. So, that is the first change which is introduced in IPv6. First and most priority was given to this particular feature, that is addressing capability. Next, we had field like checksum and many more fields in IPv4 header which were streamlined, and we made a 40-byte fixed length header. Okay, 40-byte fixed length. This is very important. This is not going to be varied. Okay. So, whatever fields we had in IPv4, only by retaining the most essential fields in IPv6, the header size was streamlined to fixed 40-byte header. Okay. That is one more change that's been introduced in IPv6. The next change, major change, is flow labeling and priority. As I already told you, we have a field called flow label and traffic class in case of IPv6. As I already told you, there is no clear distinction about flow, definition of the flow in case of IPv6. Even though it is not there, audio and video can be considered as one flow. In such a case, we need to prioritize the datagram, which datagram has to reach the destination first, which should follow next, right. So, that can be done with the help of traffic class. Using the traffic class field in the IPv6 datagram, we can specify the priority with which that particular datagram can be transmitted from sender to receiver. Or for example, we might be having several applications running on the network, right. In that case, datagram of which application need to be provided with utmost priority, even that can be done with the help of traffic class. So, with the help of flow labeling and providing the priority to the datagram over the datagram across the network, we are ensuring that the datagram which has to be reached early to reach the destination as early as possible compared to other datagrams. So, these are the three major changes that were introduced in IPv6 over IPv4. The very first one is expanded addressing capabilities, and then the second one is streamlined 40-byte header, and then we have flow labeling and priority. Having understood the changes that were introduced in IPv6, now we will look into the fields that were removed from IPv4, the fields which were there in IPv4 and those which are removed in case of IPv6. Okay. Now, we will look into the fields that are removed from IPv4 and not in IPv6. Looking at the diagram that's being displayed here, this is the diagram of the IPv4 datagram, in which we have several fields, right? When we compare this with the diagram of IPv6 datagram, we can clearly notice that these three fields were removed from IPv4 datagram. The very first is the fragmentation or reassembly field. In case of IPv6, it is clearly mentioned, or it is clearly understood that the fragmentation and reassembly of the data inside the datagram is not going to be done in the intermediate routers. Okay, it should not be done in intermediate routers. It can be performed only in source and destination nodes. So, when we say that fragmentation and reassembly of the data inside the datagram is not going to be done in intermediate routers or nodes, and it should be done only in source and destination, definitely we need not have any field with respect to these things. This results in increased speed of IP transmission. So, the transmission rate of datagram through IP has increased by removing this particular functionality from IPv6. Okay. The next field that's been removed is header checksum. As we all know that checksumming is done in transport layer and data link layer. So, there is no need to do it again in the network layer, right. So, in order to avoid unwanted functioning or unwanted process that is being done in network layer, this particular header checksum field is also removed from removed in IPv6, right. So, this also contributed a lot to the increase in the transmission rate of IP. Okay. The next field which is removed from IPv4 is options. Okay. Options is entirely removed in case of IPv6, which resulted in fixed size 40 byte header field. In case of IPv6, again when we had more streamlined header fields in IPv6, that contributed a lot to the increase in the rate of transmission in case of network. Okay, that is with respect to IPv6. So, these are the three fields which were there in IPv4 header and not in IPv6. Okay. Having understood the difference between IPv4 and IPv6, now we have two protocols, two versions of internet protocol. One is IPv4 and IPv6. As we all know that IPv4 version was the first which was used by most of the applications which were running before 90s, right. After inventing IPv6, many applications started making use of IPv6, but here we have a problem that how to communicate between IPv4 and IPv6 compatible systems. So, we are going to discuss about that now. So, the next topic that we are going to discuss is transitioning from IPv4 to IPv6. Okay. So, as I already told you, many systems in earlier days, they are making use of IPv4, right. After inventing IPv6, we started making use of IPv6, but at present we have systems which are compatible of IPv4 format, and we have many systems which are IPv6 compatible. So, how to have a communication between these two systems which are IPv4 compatible and IPv6 compatible. Now, there is a need to update all IPv4 compatible system to IPv6 compatible, right. So what is the way or what is the option through which we can make it happen? So the very easiest or the very first option that can come to our mind is flag day. Okay. This is the option which will come first into our mind. So what do we mean by flag day? It is nothing but a specific time and day which is going to be decided, and at that particular time on that particular day all the systems, hundreds and hundreds and thousands of machines, administrators, whoever got connected to internet, everything should be brought down, right, and all the machines should be upgraded from IPv4 compatibility to IPv6 compatibility. The previous flag day that has happened was around 25 years ago. Okay, 25 years ago. This was done in order to upgrade our internet from NCP to TCP. Okay, earlier internet was making use of NCP, then it has moved to TCP 25 years ago. But with the limited number of users in those days, it has made clear, or it was understood that practically it is very tough. It is not advisable, because bringing down all the users and all the network administrators and all the machines which got connected to the internet at a time is not realistic, right? It is not advisable in real time. So flag day is not an advisable option for us to upgrade IPv4 to IPv6, right? So the next option would be dual stack. Okay, dual stacking. What do we mean by dual stack? Means here we are going to develop a protocol header in such a way that it will talk in the language of IPv4 with IPv4 compatible systems, and it talks in the language of IPv6 with IPv6 compatible system. So we can represent it with IPv6/IPv4. Okay. So what does it do? When it communicates with a node which is IPv6 compatible, it sends a datagram in IPv6 format. If it finds that the next node to which it has to send the data is IPv4 compatible, then it sends the datagram in IPv4 datagram format. Okay. So it supports both. So that's why we call it as dual stack protocol. Okay. So is this a permanent solution for this problem? We'll see. Okay. When we want to communicate between different nodes which are spread across, among which few are IPv6 compatible and few are IPv4 compatible, we will just have a look. Consider an example here. We have sender and receiver A and F which are IPv6 compatible. But when I want to send an information or a data from sender A to receiver F which are IPv6 compatible, it has to go through several nodes. In between we have IPv4 compatible nodes. Here C and D are IPv4 compatible nodes. Okay. So when I send a data packet from sender A to B, it is IPv6 compatible. So there is no issues, right? And when B determines that the next node to which it has to send its datagram is of IPv4 compatible, it has to bring down the datagram from IPv6 format to IPv4. So it has to modify the header, right? So here it reaches in IPv4 datagram format. Okay. From C to D it is IPv4 datagram. So there is no problem, it will be forwarded. From D to E, even though E is IPv6 compatible node, but when we were converting a datagram from IPv6 format to IPv4 format, if you recall the fields that were in IPv4 and IPv6, several fields were not there, right? Several fields were not there in case of IPv6 which were there in IPv4, right? So when datagram from node D is getting transferred to a node E which is IPv6 compatible, several fields were dropped. So we were forced to have IPv4 datagram packet here. Okay, the same is delivered here in format of IPv4. So even though both sender and receiver are IPv6 compatible systems here, just because we have IPv4 compatible nodes in between the route from A to F, it was made forcibly, it was made compulsion that the datagram transfer from A to F in IPv4 format. So to overcome this problem, we came up with one more solution, that is tunneling. What do we mean by tunneling? So when we are transferring the data from A to F, from A to B it will be in IPv6 format, so there is no problem. From B to C, when it encountered that the next node is IPv4 compatible, then this particular nodes are considered as tunnel. Okay, these particular nodes are enclosed inside a tunnel. So the whatever datagram that we had in IPv6, the entire datagram is placed in the field of data, payload data in case of IPv4 datagram. When converting from IPv6 to IPv4 format, the entire datagram packet itself is stored as a payload data in case of IPv4. So it will pass through C and D thinking that it is just an IPv4 datagram. When it comes to know that the next node is IPv6 compatible, the data field of IPv4 datagram is being extracted and that is sent as a IPv6 datagram for node E which is IPv6 compatible, and it is transmitted further. So there is no loss of information which is being specified in IPv6 happened between sender to receiver, right? Because in case of IPv6 we introduced with fields like traffic class, right, and data flow, flow control, all those things, right. So these fields were not lost during the transmission from IPv6 format to IPv4 format. So this is done with the help of tunneling. Okay. One more thing, when we are transferring a datagram from one node to another node, how do we come to know that the next node which is in the path is IPv4 compatible or IPv6 compatible? To carry out this or to resolve this issue, we took help of DNS. We know what is DNS, right? It returns us the IP address of the given host, right? So with the help of DNS, the compatibility, IPv4 or IPv6 compatibility of the next node is being determined. If the next node is IPv4 compatible, it returns the IP address of IPv4. Okay. If it is IPv6 compatible, it returns the IP address with respect to IPv6. So by looking at the IP address that this DNS provides us for the next available node in the path, we can make sure that the next node is IPv4 or IPv6 compatible. Accordingly, the modification of the datagram can be carried over. Okay. So, this is how the transition happens from IPv4 to IPv6. Okay. The next topic that we have is a brief foray into IP security. As we all know, many users are getting into internet, right? Along with efficient and trusted users, we also have hackers in between who are going to breach the security, right? So, in order to address this issue of security, various versions of new network protocols were introduced. One among them is IPsec. Okay. So, IPsec is a protocol which has been introduced in as a newer version of IPv6, okay, to ensure more security for the data that is being transferred from sender to receiver. So, when I say IPsec is a new protocol, is it essential to have this protocol to be updated in all the routers or all the nodes in between sender and receiver? No. Sorry. We have a sender and we have a receiver, and in between we might be having several nodes, right? In this case, only if sender and receiver, if these two hosts are IPsec compatible, then that is sufficient. All the middle nodes can perform their operations either with IPv4 or IPv6. So, there is no compulsion. Okay. So, there is no compulsion to have all the routers or nodes in between the sender and receiver to have IPsec compatible system. Okay. So, we will learn more about IPsec. So, these are the functionalities that are assured by IPsec protocol. Okay. So, the very first functionality is cryptographic agreement. What do we mean by that? When we say that it is IPsec compatible host, so between two hosts, source and destination, they both enters into an agreement about the cryptography or encryption algorithm that is being used in order to encrypt the data which is being transferred from source to destination. So, the same kind of algorithm is going to be made use both at the sender and receiver. So, they both enter into an agreement which is called as cryptographic agreement. Okay. The next functionality, that is encryption of IP datagram payloads. So, whatever data payload that is going to be transferred from sender to receiver is going to be encrypted at the sender side. Okay. It is going to be encrypted using the cryptographic algorithm that is being entered into an agreement between sender and receiver. So, it is encrypted and it is transferred from sender to receiver. So, at the receiver end, using the decryption algorithm that is decrypted. So, during the transmission of data or payload from sender to receiver, the data is not going to be corrupted, or the chances of corrupting the data is less because of this encryption mechanism. So, this is the second functionality. The third is data integrity. During the transmission of payload from sender to receiver, it assures the integrity of data. Means whatever data or payload that is being transferred from sender to receiver is not changed or it is not corrupted. So that integrity of data is being assured in case of IPsec protocol. And next, the origin authentication. When a host receives a datagram at the end, that means when a receiver host receives a datagram which is sent from sender, by looking at the IP address of source, okay, looking at the IP address of source, it ensures that whatever IP address that is being specified at the source IP address field of the datagram is the actual source from which that particular datagram is originated from. So it assures or it authenticates the source from which or the origin from which that particular datagram is originated from to the receiver. Okay, these are the 4 functionalities with respect to the security aspect is achieved or is provided by IPsec protocol. So to conclude, we need not have IPsec protocol compatible nodes at all levels. Just if sender and receiver are capable of handling IPsec protocol, that is sufficient. In between, we can have any other nodes which are capable of either IPv4 or IPv6 compatible systems. Okay. So this is about our internet protocol. In the next class, we are going to discuss about the routing algorithms. Okay, we are going to study more about the routing algorithms with which we can route all these datagrams from source to destination across the network. Thank you.